continue straight from last video where we calculated the I effective average 227 times 10 to the power 6 millimeter power 4. Now we like to calculate the long-term deflection after the attachment of the deflection sensitive partitions. Now this is little bit different than what we done the deflection in the beam examples in the previous videos, where in here they say that in the questions limit the incremental deflection after the attachment of the brittle partition. That's the limit. So it says that incremental deflection here. So we need to see that incremental deflections due to the attachments. So incremental deflection, so we need to find this incremental deflection total is equal to short-term incremental deflections plus these creep and shrinkage factors times the short-term deflection due to the sustained loading. So I can describe these each parameter one by one. Delta S increment, which is the difference between the short-term deflections. We know how to find the short-term deflections due to the short-term load, but we need to find this one. So we take the difference between two deflections, one for this short-term load and one for this incremental load. That's just the dead load that we're going to look at in a minute. Now this is creep and shrinkage factors. We done the previous videos how to find it. I will show it to you again here, and this is the calculation which is same as we done it in the previous videos, which is the short-term deflection due to the sustained loading. Now let's I already explained that this is a sustained loading due to this sustained long-term load. This is short-term deflections delta S. Now let's work it out, the short-term deflections delta S due to this short-term loading. So this is an equation. I think this equation is given in the books. I think it's not given in the standards. It's just obtained from the structure analysis for calculating the deflections due to the in the continuous multi-story span, multi-span. Length we already discussed. The length of the span is the span length is 5.05 meters. So I substitute that one here. 96 times the Young modulus of the concrete. I effective average we just calculated in the last video. I substitute that value here. The moment at the left support is 0 plus 10. Moment at the mid span is 10.9, and this multiply by 10 raised to 6 to convert into Newton millimeters. I think in the previous video we calculated mm. And minus 19.5 times 10 to the power 6, that is the moment at right supports. We done in the past videos we calculate this one as well. So this is 4.8 is the short-term deflections due to this short-term load. Now there is one more terms that is new that will not cover in the last deflection video, which is the delta G, which is the short-term deflections incremental. This is the new word, incremental short-term deflections due to the load WG. Now we already know the deflections delta S due to this loading, so we can just take the ratio, this incremental deflections over the short-term deflections equal to the respective load over the loading that we are using it here. It's just a ratio, deflections over the deflection over the respective loading over the loading. So if you just simplify that, if you simplify this one, you have 5.7. I think this one is just a dead load. I think in the previous video we know where it is 5.7 over 7.1. That is also we calculated here in the previous videos. We can just have this dead load plus short-term factor 0.7 times the live load. I think we calculated dead load and live load and short-term factor 0.7. That simplify give me 7.1 times 4.8. We just calculated that one, so it's give me 3.9, which is the incremental deflections due to this load. So if I want to calculate this short-term incremental deflections is equal to this 4.8 short-term deflections due to this short-term load, take away these incremental deflections due to this late load, which is give me 4.8, take away 3.9 is given 0.9. That's we need for this calculation. So we calculate this first one. Now let's calculate this delta sustain, which is a short-term deflection due to the sustained loading. So that is called long-term, that is due to this long-term service load. Now long-term service load is same as short-term service load, only difference is this psi s and psi l. Psi s is short-term factors and this is long-term factors. So 5.7, that dead load we calculated in the previous videos, plus 0.4 is the short-term and long-term factors. I think that is given in our questions. That is given in the questions, both short terms and long term. So we are using this 0.4 times 2 is equal to 6.5 kilonewton per meters. Now we know already 4.5 for this loading. So if you have 4.5 for this loading, so we can just take the ratio. We take the ratio delta sustain that we need to find. I think this delta sustain that we need to find. So deflections due to the long-term loading, so that is deflection over this deflection is equal to respect. So there is two deflection ratio equal to respective to loading for those deflections. So if you just simplify that, delta S sustains is equal to this 6.5. We just calculated this long-term service load over short-term service load. We calculated in the previous video is just 5.7 plus 0.7. Where is 0.7 come from? That is 0.7 times 2, it's give me 7.1. So 6.5 over 7.1, this deflection we just calculated 4.8. So delta sustain is 4.4. So we calculate those two parameters. Incremental deflection 0.9, delta sustain is 4.4. So we can calculate now KCS. KCS is basically this in this clause 8.5.3.2, it has given you this KCS is equal to 2 take away 1.2 area of the compression reinforcement area over tensile reinforcement area. We don't have any compression reinforcement, so that is 0 over tensile reinforcement times 1.2 is 0, so it's just 2. We take the previous videos where we have detailed discussion of KCS, but here we will have KCS equal to 2 is greater than 0.8, so that is okay. Now we have all the required parameters to calculate these delta totals, the long-term deflections, which is delta short-term deflection, incremental short-term deflection plus the creep and shrinkage factors times the short-term deflections due to the sustained loading. So 0.9, we have calculated this 0.9 millimeter, that is short-term incremental short-term deflections, that I substitute 0.9 here. KCS we just found here, and this delta sustains we found 4.4, that I substitute here. So the answer is 9.7 millimeters, that is the deflections. Now limiting deflections, the standards generally give you this limiting deflections delta over 250, that is typically, but in the questions they have give you already this limitations, which is 1 over 500. So L0 over 500, L0 we know 5.05 meters, so just convert into millimeters over 500 give me 10.1 millimeters. So 9.7 is less than 10.1, so that is okay. That is the maximum deflections, allowable maximum deflections. So that is the 10 point. We can't go more than that, but our deflection in the slab is 9.7, so that is okay. Now one notes, a slab depth of 190 millimeter is therefore acceptable. So if you know that slab depth we calculated here, that will that is okay for the deflection check. If the slab shape should not prove to be satisfactory, let's say you have more deflection here, let's say you have 50 millimeter deflections, that will not be satisfactory, then a revised trial depth is selected. So then you need to increase this depth, let's say 220, 230, and you need to repeat the whole process again. Generally structural engineers use the Excel, they develop the Excel sheet to do this iterative process and have an economical and optimized slab depths. We continue solving these examples further in the next videos. Thank you.